Hey there, this is Qasim Wani, and welcome to another video in the reinforcement learning series. Um, in this video, we'll talk about priority experience replay and some of the approaches that the Google DeepMind team has taken in regards to that. So this video will be split in two parts. The first being the first part being about the general idea of experience replays, and after that, the alternative method on building a more robust and better approximation towards the optimal policy using prioritized experience replays as one of the ways to build a better DQN. In the previous video, we looked at how to build a better Q table using a double Q learning algorithm, and how you can use that to build a better DQN network as well. And in this video, we'll be sharing some ideas and key findings of the Google DeepMind's paper on prioritized experience replays. Without further ado, let's just dive into sort of the two slider I have on this topic. And sort of the slides that I'm using are from Udacity's Deep Reinforcement Learning Nanodegree. So these are not my own. The pictures that you see are not mine, but sort of the explanation and intuition is sort of my input. Yeah, so let's talk about the experience replay buffer so far. Just a general idea behind it, right? And the idea behind using a buffer has key components, and we'll get into this later when we look at the paper on the prioritized experience replays. The first idea is to split off the correlation between consecutive states or consecutive experiences, right? And the idea is that when you're sampling an episode, you're getting states S of t, and then the next state S of t plus 1, and so on and so forth. And there is a positive correlation between the action that you're going to take, the action that you're taking at the current time step, and the immediate effect it would have on the next state, right? And so the way you think about it is, if I'm performing, given the current state that I'm in, and I'm performing an action A, the next state is highly correlated with the action that I just took, right? And so the way you think about it is that this state, A of t, directly impacts S of t plus 1. And so the action that I've taken, A of t plus 1, will directly impact the state I would be in for S of t plus 2, and so on and so forth, right? So this idea that the current action that I'm about to take with the immediate reward that I would get from it is a direct correlation, a positive correlation to the next state that I will be in. And this correlation sort of creates this bias for our learning algorithm. And the reason for it is because you want to gain an independent understanding and relationship between the action and the state for a Q table, right? The action value is supposed to gain independent understanding of the experiences that you gain. And this correlation creates this implicit bias in your learning algorithm. And the way you solve it is by sort of removing the correlation between consecutive states in an experience or consecutive experiences. And you do that by sampling at IID the tuple of state, action, immediate reward, and the next state, right? So basically SARSA, except for the next action that you'll take place, because you're technically using this for your TD algorithm or your TD control or your DQN network. And so the idea is to split off essentially shuffle in mini batches. Sort of if you're coming from deep learning, you're basically using a mini batch to sample through at random, such as to maintain IID properties of the sampling distribution of your buffer being independent and identically distributed, right? And now you have your state of A, the first state, the chances of it correlating with the second state is very unlikely. And this is perfect because now we have gained sort of this independence between two consecutive states, and our algorithm will learn a much better approximation that isn't biased by this correlation, which prevents from overfitting of our model. And so that's the idea of the experience, why we're using experience replay buffer, right? And so the core, and so the thing is, you know, now the experience buffer sort of makes sense. That was the motivation behind it. What are its potential fallbacks? Where can it not perform as well? And we'll cover this with extreme details in the second part of this video. In the first part, there's two reasons why. The first being that some experiences are more valuable than others. And most importantly, some experiences that are hard to come by are going to be treated with the same level of priority as any other experience in your buffer. So let's dive into it in more details, right? The first statement was that you're sampling every single experience with the same frequency, right? If you're using the normal distribution, right? If it's coming off through the Gaussian, sort of the normal distribution graph, every sample is has an even likelihood of occurring, or of being sampled. And this is a problem because some experiences that are more rare and of high value are not going to be sampled as frequently as samples that are more frequent in general, and also do not provide that much significant amount of learning. So that's the first problem with using a buffer like this. The second is the fact that these buffers are of limited size, right? So you can think about it as a deck, sort of a data structure, right? Because you're trying to use a double-ended cube sort of to make it a circular list and essentially sample through the last n tuples of state action reward collections, and you're trying to sample through a circular amount of them with a confined limited size. And an experience which you experienced at the first state will, although it has, you know, even likelihood as being learned from in your mini batch when you're sampling through these at random, it has a much smaller chance of being resampled. In fact, it has a 0 probability of being resampled as the number of episodes that you're learning from increases. So what that means is, initially, when I am going through the first episode of the MDP process, given it follows the GLI conditions, the first episode's first state action that I have just taken is definitely going to be at random through the epsilon greedy approach. But that collection, right, could be confined into this area. And since this is a buffer, the knowledge that you gain at this state is only limited to the buffer size of 2000. Let's say the buffer size is of 2000. So you're sampling, you're restoring your buffer every 2000 iterations, right? And let's say one episode has, since it's an episodic task, you're going to continue into that episode until it terminates. And let's say in that episode, you run it for 10,000 times. So this learning, this point will be removed from the buffer at 0.2000 or 1999 if you're zero-based indexing, right? And so you have the ability to learn from this only from point 0 to point 1999. And, and you're only able to learn from it from many batches that you select from it. It could be a size 64 or 32. Generally keep your mini batches in powers of 2. And that is derived from the sort of the convolutional neural net, or the approaches from the CNN with Jan LeCun and his work in this field of batches and mini batches. And so that's the idea, right? The problem arises when this point is of significance, but it'll be removed completely after the 2000 episode or the 2000 experience, and you no longer have the ability to relearn from it. And so those are the two problems with experience replay buffers, the traditional way that you learn. The first is some experiences are more valuable than others, and so they should be learned from multiple times or with a higher priority than others. And the second being that experiences that we serve through initially have a very small likelihood of being resampled as the number of episodes, as the sort of the and the agent keeps learning and learning. So we're risking information, and we're risking what information to choose at a time step t. And to combat that, we introduce this idea of a prioritized experience replay buffer, right? And the idea is that it combats both of these. The first being, it places a priority on experiences that are more important or valuable. And the way it does it is by introducing sort of the priority for a state or for a collection based on its TD error, right? So the error that you have based on the current value from the Q table with respect to the actual target. So the error between the target model and the normal model, and that can be characterized as a TD error, which you see right here, right? So you have your target model and your old or the normal, the main model itself, right? And the greater the error, the larger the error, the more there is to learn. And so this idea can be your motivation for that state action pair to have a higher priority, right? If there's more to learn from an experience, maybe sample that more times. And that is the idea behind using the sort of priority behind it. But now, what happens if the error is very small, right? So delta, as it approaches 0, you're unlikely to actually experience that sample again, except for the first time that you encounter it. So the idea is to always make sure that you're sampling experience at least once, and that is the first time that you encounter it, you're sampling it by default, right? But what happens now if you're only sampling it once, even though that means if you're sampling it once and there's a very small error, that means your value, your function value approximation at that point for that sort of state action value pair is pretty good. It's a good estimator. But there's still, you don't want to run the risk of overfitting your models to only elements with high priority. You also want sort of this balance between elements with lower priority, right? So this can create an overfitting for your model. And the way you do it is by introducing sort of this constant epsilon or E, which is basically a hybrid parameter which you can tune to sort of bias your limit, your minimum priority, right? And this sort of plays into how your buffers would shape up. And now, instead of a replay buffer with just 4 samples, the SARSA, except the last action, you now have the current state action that you would take for that state, the immediate reward, the next state, and the priority for that state action pair. And what you do essentially, you use the same mini batch from this buffer of size n, but instead of sampling uh, at random with uniform distribution, now you're going to sample those with a higher priority, uh, essentially, right? And and you can now see that this also creates a bias of itself, right? If I'm only sampling the higher ones, I'm running the risk of not sampling ones that are of lower priority. And the reason is because sampling just from the higher elements from just higher priority creates an overfitting for a model. And we want to make sure that it follows the IID, because now it fails the distribution curve, and now the samples, the elements are not sampled at random. Right now, there's a strict policy that you're using for sampling alone, so it fails the basic IID condition, right? And the way we combat that is by using what is known as a give me one second. So the way we combat that is by using the sampling probability, and which is over here, such that it's a stochastic measure of the probability of each individual element. But at the same time, the way we do that is by updating our gradient descent by using something, by using a weight known as the importance sampling weight. And we'll cover all of this in great details in the next video, which talks about the DeepMind paper. And the idea is to sort of tune your sampling rate, sorry, not sampling rate, but the proportion you're using for sampling. You can tune that to go from something known as a proportion-based prioritization to rank-based prioritization. And this is covered in the DeepMind paper. So what happens is we will use a sampling probability to sift through what experience to extrapolate, but we'll use a parameter alpha, which would help in sort of understanding which one of these tuples to take from the replay buffer, right, through our mini batches. And the way you do that is by setting an alpha over here. And one thing to note is that if alpha equals 0, we're sampling from a pure IID distribution, right? Because now it's just 1 over 1, ergo, 1 over the summation of the priorities, which is basically a summation of the replay buffer. So 1 over the size, meaning that every single tuple is equal, has an equal likelihood of occurring. Therefore, IID condition has been satisfied, and it follows a normal distribution graph. The second being, if alpha equals 1, then we are only using the priority values, right? So if alpha equals 1 is literally just the one which has the highest priority will get sampled first, regardless of so the one with the highest priority will get sampled first, the second one, and so on and so forth. And so if you have a mini batch of size 32, you would have the 32 most sampled elements. And so that will always, and that would be a recurring thing, right? It's not that you're just getting rid of those. You will get rid of those after the replay buffer gets saturated and gets restored. But until then, if you have a size of, let's say, 2000, it would get sampled 2000 by 32 times, right? Which is like 15 or so. So that's sort of the idea behind, like 30 times, my bad. So yeah, that's the idea behind using this parameter alpha, and this is a hybrid parameter which you can tune. The other idea is to use a modified update rule, and this is basically gradient descent, right? When you're updating your weights through your deep Q network, instead of doing it how we did it normally, which is by taking in the error and using that as the sort of the gradient of the Q prime or the Q star, the target that you want to sort of optimize for based on the parameter W. You will now also introduce this weight called the importance sampling weight. And not just that, but you'll also introduce another hyperparameter known as beta. And what happens is that as the number of, as your Q value sort of starts to converge into the optimal policy, your beta becomes more and more significant and ultimately closely reaches a score of 1. As the number of episodes, as the number of experiences approaches infinity. And so that's the idea behind prioritize experience replays before. No, sorry, just the experience replay in general, and how to fix the problem with experience replay using the prioritized experience replay. In the next video, I'll discuss the paper shared by Google DeepMind on this exact topic, and we'll go into much details on how it's done and sort of the intuition behind using this, and revisit the ideas that we mentioned in this video directly through that paper. And so that's all I have for this video. If you liked it, make sure to watch the part 2 of this sort of mini series. And if you enjoyed it, make sure to subscribe and share this content. Cheers.